All right, kids. So I'm going to go through a couple of practice problems. I think three actually. And then I'll also make a second video of your worksheet. Okay. But that's your Monday assignment to watch the practice problems if you need to, and then do the electrochem problems. Okay. So I have a split screen here. On the right side is the table of standard reduction potentials. So I will actually attach this as a PDF into your chapter 20 module on Canvas, because this is probably the most comprehensive standard reduction potentials list that I've found. It's from my textbook. The one in your textbook is much shorter, I believe. Maybe the one in the back is better. But yeah, this is probably the best one. You just find portions of this online, but AP will give you the specific reactions you need, so you don't have to worry about knowing like anything on this table. The references will be given to you, okay? But all the questions will require you to use most of these, so that's why, not most of these, but some of these. That's why I will upload a PDF of this, okay? So here's practice one. The work is already there, but let me walk you through the problem. So it says to use the tabulated values. The tabulated values are on the right, to calculate the standard cell potential for a reaction. So you know the way to calculate standard cell potential is just E cell is equal to cell potential of the oxidation plus the cell potential of the reduction reaction, right? So it's a little noisy. It's because cafeteria just let out people. Okay. So this particular reaction, aluminum nitrate, hydrogens going to aluminum 3 plus, nitrogen monoxide, and water, this is actually already balanced in terms of atoms and also charge. Okay. On the reactant side, we have a total charge of +3, and on the product side, we have a total charge of +3 coming from the aluminum. So you just have to identify, if it wasn't balanced, you would have to balance the half reactions based on acidic or basic solution. If they don't say basic solution, it's usually in acidic solution. Okay. So you just have to figure out what's oxidized, what's reduced. So you have aluminum with a oxidation state of 0, and it becomes +3 here. And then if you look for nitrates, nitrogen, oxygen is -2. -2 times 3 is -6. So nitrogen must be +5, because we need to have a -1 charge at the end. And then this is -2, therefore nitrogen has become +2, which means nitrogen or nitrate is the thing that has become reduced, okay, from +5 to +2. So you write your half reactions out, and it's not always necessary to write the half reactions out, because you can actually use the table to get your half reactions and the values for them, okay? So let's look at the standard electrode potentials for aluminum's oxidation. I think it's down here. Yeah. So aluminum really likes to be oxidized, which means on the reduction table, it's going to be pretty low, okay? And here it is right there. That's aluminum plus 3 electrons going to aluminum solid. That's the reaction you're looking for, right? Aluminum becoming aluminum 3 plus is going to require 3 electrons. However, this is a reduction table, which means you are looking for the oxidation reaction, and the oxidation reaction is going to be in reverse of the reduction one. So that means you are looking to reverse this equation. If you reverse the equation, you must flip the sign, okay? So -1.66 becomes +1.66 for the oxidation of aluminum. And then you can find the one for nitrate up here. It is 0.96 right there, 0.96, and that value you keep as it is. Remember, any value that is above the standard hydrogen electrode, which is right here, is going to be positive. That means it likes to be reduced, and any value that is below that is going to be negative for reduction potentials, and that is going to want to be more oxidized, okay? So EOX plus E reduction gives you 2.62 volts for the cell potential of this particular galvanic cell. All right, let's look at the second problem. Well, before that, I actually have a trick to teach you. I forgot that this existed. So here's how you predict the spontaneous direction of a redox reaction. This is a little trick, okay? When you look at the two half reactions, if you don't want to do any calculations, you can easily do the calculations to figure out if it's going to be thermodynamically favorable. If your E cell is positive, that reaction is thermodynamically favorable. Okay, that's basically the rule. If positive E cell, your reaction is favorable. So like the previous problem over here, this one is thermodynamically favorable because it's 2.62 volts positive. Okay, so here's how you do this without actually doing a calculation. This is really only useful if you have the standard reduction potential table with the correct order of things, with the numbers properly arranged. Okay, like usual standard reduction potential table will have everything in order, but you may not get it for the AP exam. So all you have to do is you look for your forward reaction and you look for the reverse reaction. So one has to be forward, one has to be reverse, right? So let's look at the problem that we were examining just now, nitrogen being reduced and oxygen, aluminum being oxidized. So the forward reaction, the forward half reaction on the reduction potential table has to be paired with something below it. So I call it the clockwise circle of redox. So you draw your circle clockwise over the nitrate, over the aluminum. If you are going this way and the top is the reduction half reaction, and the bottom is the oxidation half reaction. Okay, that means you are going to have a thermodynamically favorable electrochemical cell. So the reduction reaction, the reduction half reaction has to be above the oxidation half reaction. And remember, oxidation has to go in reverse, which is why this is clockwise. Okay, I call it the clockwise circle of redox. And anytime your reduction is above your oxidation reaction, and when you're going clockwise through them, you have a thermodynamically favorable electrochemical cell. Okay, so that's a way to just do it without doing any math. Just look at the places, but obviously you need a proper table to do that. Okay, they used to give you the whole table, but they just don't anymore. I don't know why. Okay, now let's look at these two equations. We are trying to predict the direction of the redox reaction. And if it is redox, that's thermodynamically favorable, you have to draw the galvanic cell. So over here, iron is going from 0 to +2, that's oxidized. Magnesium is going from +2 to 0, that's reduced. So let's look at the locations of iron and magnesium. This is iron 2, don't mix it up with iron 3, okay? Let's find iron 2. Aha, right there. That's the one that I will mark in green. So here's iron 2. And in this particular case, iron is actually getting oxidized. So iron's direction is this way. Remember, this is a reduction table. And magnesium is being reduced to go this way. So the reduction half reaction has to be above the oxidation. But in this particular case, this is going in the counterclockwise direction. As you can see, oxidation is above the reduction. Okay, and that's no good. It has to be reduction over oxidation, not oxidation over reduction. Just even before you do any calculations, negative 0.45 is going to be positive 0.45, and then the reduction one is negative 2.37. The more negative value is going to want to oxidize, not be reduced. This is not thermodynamically favorable. And here's the justification in yellow on the slide. Okay, the calculation is right there. So this is not a thermodynamically favorable reaction. Let's look at the next one. We are looking at, let me erase this. We are looking at iron again. So iron is going from 0 to +2. And then lead is going from +2 to 0. So lead is being reduced, iron is being oxidized. So the thing that is oxidized has to be below the thing that is reduced when you're going clockwise, right? So the thing that is being reduced is lead 2, right there. So lead is going in the forward direction. And then iron is below it going in the reverse direction. This is the oxidation of iron 2, and this is the reduction half reaction for lead. So lead will go forward, iron will go reverse. This is a clockwise circle of redox. This is thermodynamically favorable, and you can justify it using the calculation. It's 0.45 plus negative 0.13 volts is equal to 0.32 volts. It's positive value, thermodynamically favorable. Okay. Also, lead is lead is more negative. Lead is less negative than iron. Like lead's reduction potential is less negative than iron, which means it is the one that wants to be reduced. And iron being more negative than lead is going to want to be oxidized. Okay, whichever one has more negativity is going to want to lose that negativity to become zero, which is what a free element is, right? So iron, that's kind of how I think about it. It's a qualitative thinking. It's not really that they're trying to get to zero. Okay. If you can think of it that way, whichever one is most negative is trying to lose some of that negativity, so it gives up its electrons, and whichever one is more positive, because oxidation states are made up, right? Whichever one is positive is trying to get rid of that positivity to become closer to zero. So if you're negative, you give away your electrons and you become oxidized. If you're positive, you're more likely to accept electrons to get to also cancel out that positivity. Okay? All right. So here's a conceptual question right here. I was in the midst of typing some stuff, but we can just use the table for this. So a solution contains sodium iodide and sodium bromide. Which oxidizing agent? So the vocabulary is really important here. Oxidizing agent means that that thing is going to be reducing whatever. Oxidizing agent means it's a reducing, it'll undergo reduction, but it will be oxidizing the thing that it is reacting with. Okay, there we go. Okay, so oxidizing agent will become reduced, is what I want to say. It'll become reduced. There we go. When you add it to iodide, but you don't want to oxidize bromide. So it has to be something that will become reduced. That means it has to be above iodine, but below bromine, right? Because you don't want to oxidize bromine. If you want to oxidize something, that means you're going to become reduced yourself. That means you have to be above the thing that you're oxidizing, okay? So chlorine, in this particular thing, chlorine is all the way up here. Chlorine is a strong oxidizing agent. Chlorine, being all the way up here, is actually above both bromine. So bromine is right here, and iodine is right here. So because it's above both of them, it'll basically oxidize both of them. But you don't want to oxidize both of them. Then hydrogen peroxide, where is that? I wonder if hydrogen peroxide is in this. Oh, it's even higher than chlorine. So it's going to oxidize both bromine and iodine. And then copper chloride. So it's not chloride. It's not copper. Let's find copper. Okay, so copper is below. It's not the chloride. Chloride is not going to do anything there. Copper chloride contains chloride ions, okay? It's actually the copper. Copper can't do anything to either iodine nor bromine, because both versions of copper, well, this is copper 2. The copper 2 is below both of them. So that is not an answer either. So the only answer left is the nitric acid there, because nitric acid, let's get this color. Where is the nitrate? Oh, right here. So look, this is nitrate. Nitrate and hydrogen will form nitric acid, right? So nitric acid will actually selectively oxidize iodine, make it go this way, because this reaction will go in this direction. As nitrogen in the nitrate becomes reduced, iodine will become oxidized. But because nitrogen in nitrate is below bromine, it is powerless against bromine. Okay? So the reduction of nitric acid is below the reduction of bromine and above the reduction of I2. Therefore, I2 can be selectively oxidized, or iodine can be selectively oxidized by nitrogen, and not bromide will not be affected. Okay?